Hello everyone, and thank you for attending today's webinar. My name is Jeff Kenvin and I'm the Technical Director at Micromeridics Instrument Corporation. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple engagement tools you can use. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A. We'll try to answer these during the webcast, but if we run out of time, it will be answered later via email. Additional materials are available in the resource list. We encourage you to download any resources or links that you may find useful. Some networks cause slides to advance more slowly than others, so logging off of your VPN is recommended. If your slides are behind, pushing F5 on your keyboard will refresh the page. If you experience any problems during the session, you can find answers to some common technical issues located in the Help Engagement tool at the bottom of your screen. An on-demand version of the webcast will be available after today's webcast and will be emailed to you once the session has concluded. I'm pleased to introduce today's speaker, Dr. Jacek Jagiello. Dr. Jagiello is currently a senior scientist at Micromeridics. Jacek's current research is focused on advancing the characterization of porous and non-porous materials using experimentally obtained gas adsorption isotherms in combination with 2D finite NLDFT models for heterogeneous surfaces. Jacek has more than 150 publications and currently enjoys a Hirsch index of 49. Jacek, it has been a pleasure collaborating with you for more than a decade and a true honor for me today to introduce you. We are so glad you could be here today to share your insights on exploiting multiple gas adsorption isotherms for consistent pore size analysis.
Thank you, Jeff, for your kind words and for giving me the opportunity to talk about adsorption-based characterization methods of porous materials that I studied for many years. Thanks everyone for joining this webinar. I will begin by introducing basic concepts of modeling of physical adsorption on porous solids. For this modeling, we use NLDFT, that stands for the non-local density functional theory. I will illustrate the process of modeling a theoretical adsorption isotherm and using the family of such isotherms to calculate the pore size distribution of a sample of porous solid. Most of the models discussed in this presentation are developed for porous carbons, zeolites, and silica materials. I will discuss the improvement of the standard one-dimensional NLDFT model for nitrogen by introducing the 2D NLDFT version of this model. In the second part of the presentation, I will explain the dual gas analysis method, and finally, I will present examples of application of other gases used as probe molecules for the PSD analysis. From the molecular view of adsorption, we understand that the gas molecules adsorb on the solid surface because the interaction between gas and solid is stronger than the interaction between gas molecules. The presented gas-solid potential was obtained for argon interacting with the surface of graphite. But this shape of the potential is representative for any simple gas molecule interacting with flat solid surface. The distance from the surface is scaled in molecular units, Z divided by sigma, where sigma is the diameter of an atom or a molecule. It is characteristic for this potential that it has a minimum at about 1 molecular unit from the surface, which means that this is a position where the molecule is just sitting on the surface. It's just on the surface. At this position, the molecule has the strongest interaction with the surface. It is also characteristic for this potential that the interaction is relatively short range. It goes to zero at about 4 molecular diameters. The gas-solid interaction potential is called an external potential. For porous material, the external potential is defined by the solid structure and the shape of the pores. In modeling of molecular system by using density functional theory, we have to mathematically describe all the interactions of the system, including the external potential that we just talked about in a previous slide, the interaction between gas molecules which are included in the free energy functional, and in this way we obtain the functional, which is called grand potential and has nice name omega, and this omega describes the whole system. Now, we can use omega to calculate the density profile at equilibrium conditions. And this is done by minimization of omega. So the minimum of omega gives the density profile of the system that we model. This slide illustrates modeling of very simple system, which is argon on graphite. The bottom graph shows the external potential that we discussed before, and the upper graph shows the calculated density profile for this potential. At very low pressure, we obtain the small peak at a distance of 1 molecular diameter from the surface. And this corresponds to the minimum of the potential. Now, when we increase pressure, this first peak becomes larger, but we also obtain a second peak. Second peak represents the second layer of adsorbed argon. Now, if we increase pressure even more, we obtain more peaks corresponding to more layers of argon on the surface. So, if we want to relate this process to classical methods, we can say that first peak corresponds to monolayer adsorption described by Langmuir equation, and multilayer adsorption corresponds to the BET equation, very well known. Here we illustrate adsorption in a slit pore. Slit pore is created by two layers of graphite that are in parallel. So here is one layer, here is the second layer or surface of graphite. So the potential of such pore is very symmetrical. Now, it has two minima in this case. The upper graph shows the density profiles calculated for different pressures, for increasing pressures. So the lowest pressure gives this kind of density profile that, as we expected, would have sharp peaks corresponding in the position corresponding to the minima. The adsorption isotherm calculated from this density profiles is shown on the right. So each point in each blue point on this plot corresponds to different density profiles shown here. So the first blue point corresponds to the first density profile. Once we increase pressure, we obtain a second density profile which has only two peaks, and this corresponds to the pressure point here on the isotherm. Then, if we increase pressure even more, you will see the small little peaks near the main peak corresponding to the minimum of the potential. We notice the density profile in the center of the pore is 0. Then, if we increase pressure even more, we will have this second peak will grow, and then we'll obtain a third peak near the wall, and this would be a point here on the isotherm. For even higher pressure, we see a condensation in the pore, in the center of the pore. This density profile corresponds to the isotherm point up here. Then the following points on the isotherm correspond to increasing density inside the pore. As we said before, the external potential is a very short range. So the initial density profile shows just one peak near the wall. Then there is a second peak, and in order to obtain condensation here, we should take into account the interaction between the molecules that are already adsorbed. So this condensation range is due to interaction between adsorbed molecules, because the external potential does not allow for additional adsorption. So what is in the middle of this pore is due to interaction between adsorbed molecules. Now that we know how to calculate theoretical isotherm using density functional theory, we can calculate many of such isotherms for a sequence of pore sizes like it's shown here. This set of isotherms may be called a family of isotherms, but mathematically it's called a kernel. To calculate the pore size distribution from the experimental isotherm, we fit the kernel to that isotherm. And the fitting procedure is here that I call jokingly in the black box. The fitting procedure is conditional. That means that there are conditions applied to the fitting, and the condition is basically introduced by regularization procedure. So after the regularization procedure, the result is obtained in the form of pore size distribution shown here. The effect of regularization procedure is illustrated in this graph. So in case of no regularization applied for the calculation of pore size distribution, we would obtain this noisy dotted line shown here. The optimal regularization gives nice smooth curve shown here as a continuous line. It's not only smooth, but what is important, this solution is stable. That means the minor changes in the data in isotherm would not affect significantly the calculated pore size distribution. For the optimal regularization, we use the method of so-called L-curve method, which was developed by the scientists of statistical computation. First ever application of density functional theory to characterization of porous materials was for carbons. In that study, Nigel Seaton group from BP used perfect slit pore model with a simple version of density functional theory called local. In the following works, the theory was improved by using non-local density functional theory, but the model of carbons remains the same slit pore model. Slit pore model was also used in combination with kernel obtained by Monte Carlo simulation for studies where the molecules of different sizes were used to analyze the network connectivity. The molecules used were CF4 and SF6. Many other studies used slit pore model for the analysis of pore size distribution of carbons. But when the experimental data became higher quality, higher resolution, people start to observe the deviations from by fitting the experimental data, obtain deviations, and corresponding pore size distributions show a minimum at about 10 angstroms for any carbon. And this was concluded that these artifacts were due to layering transition here in the kernel which is obtained for the perfect slit pore model. An important step in understanding structure of nanoporous carbons was made by scientists from Oak Ridge National Lab. They reported atomic resolution images of carbon material taken in different places of the carbon sample. These images show segments of defected curved graphene sheets. The authors concluded that graphene sheets that are defective and curved are actually building blocks of nanoporous carbons. The atomic resolution images of nanoporous carbons shown in a previous slide are very impressive, and the conclusion about carbon structure based on graphenes is convincing. So we were inspired by these results, and we modified the standard slit pore model by introducing heterogeneity and corrugation to the pore walls. This can be done by extending one-dimensional model for slits to two-dimensional NLDFT model for heterogeneous slits. And the kernel obtained by this model here is very much different from the previous kernel of standard pores. So it does not have any layering transitions, and the fit using this model is perfect. There is no deviations, and on pore size distribution there is no minimum at 10 angstrom. Actually, at this point there is a maximum on the new distribution. So this model, this 2D NLDFT model for carbons, is available in micromeretic software, and this is significant improvement over slit pore model. It is well known that measurements of nitrogen adsorption isotherms at 77 K on microporous carbon may be extremely time-consuming, especially when the sample contains ultramicropores. Such measurements may be sometimes inaccurate when the adsorption equilibrium is difficult to reach due to very slow diffusion into such small micropores. Historically, CO2 adsorption isotherms measured at 0 degrees C were used for the analysis of such carbons, usually carbon chars. However, CO2 isotherm at this temperature is only sensitive to pores smaller than 1 nanometer or 10 angstrom. So, the full pore size distribution cannot be determined by this method. For the analysis of microporous carbons, we developed a dual gas analysis method in which we simultaneously fit the 2D NLDFT kernels for CO2 and nitrogen to the corresponding experimental isotherms, and in this way we obtain the full pore size distribution for the analyzed carbon. An example of such analysis is presented by this slide. Here we measured nitrogen and CO2 isotherms on a series of samples derived from PET by pyrolysis followed by activation with CO2. We obtained excellent fit to CO2 and nitrogen isotherms for all samples. This demonstrates the consistency between the two kernels. The calculated PSDs show here the expansion of pore sizes from very narrow to broad for highly activated carbon. Very narrow is for non-activated, just pore. Very narrow is just for pyrolyzed. The fact that CO2 adsorption isotherm is sensitive to small pores implies that this isotherm provides information about these pores to the common distribution obtained from both isotherms. The same information is provided by the low pressure part of nitrogen isotherm, so if this low pressure part of nitrogen isotherm is not measured, our dual gas method can still provide the full pore size distribution. This slide shows the comparison between the result obtained by two cases. In one, the full nitrogen isotherm is measured, and in the second, just a portion of nitrogen isotherm is measured. And the calculated pore size distributions obtained from these two cases are almost identical. Practical benefits from these methods are that we can significantly reduce the time of the analysis of microporous carbons, and that we can use the instrument like TriStar that does not measure low pressures. For more sophisticated analysis of pore accessibility, the full and nitrogen isotherm still needs to be measured. This study was presented in that paper that I don't have time to give full details. For years, nitrogen dominated the PSD characterization of porous materials. However, nitrogen has a high quadrupole moment that may interact with the surface polar groups and influence adsorption isotherm and thus distort the calculated pore size distribution. The IUPAC technical report of 2015 recommended Argon at 87 for the PSD analysis as it is neutral to specific interactions. However, using liquid argon as cryogen for argon adsorption is expensive in various parts of the world. We propose using oxygen at 77 K for the PSD characterization of porous carbons. The quadrupole moment of oxygen is 1/3 of that of nitrogen. So for the analysis of oxygen, we can use liquid nitrogen, the standard liquid nitrogen as coolant. To support our idea of using oxygen for characterization, we analyzed several representative carbons using 3 gases for analysis. We used argon, nitrogen, and oxygen for this analysis. We obtained excellent fit to all isotherms studied. And the calculated pore size distributions obtained from 3 different gases show very high similarity. So using oxygen, we obtain actually almost the same pore size distribution as from argon or nitrogen. Actually, nitrogen is differing the most from argon, which argon is supposed to be the most accurate. This slide shows some modeling details of adsorption of oxygen and argon. So we have the kernel of oxygen and argon. They are quite similar. Of course, the temperature is different for both isotherms. Now, it is interesting to observe the density profiles, the local density profiles for both gases. Since oxygen is at lower temperature, we can see more clearly the positions of molecules because they are more localized. For argon at higher temperature, the positions are more diluted. So it's just to show, this slide is just to show some background of work of modeling of these gases. Last year, we developed a second version of the dual gas analysis method using hydrogen and oxygen. We realized that CO2 in the first version has quadrupole moment even higher than nitrogen. That makes it highly susceptible to the interaction with polar groups on the surface. Hydrogen quadrupole moment is much lower than that. Hydrogen at 77 K is a quantum fluid, so we introduced Feynman-Gibbs quantum corrections to the kernel calculations. The correction slightly reduces values of the isotherm. Looking at both kernels, we see that they are qualitatively similar, but hydrogen isotherms are shifted to lower pressures compared to CO2 isotherms. Sensitivity of the hydrogen isotherms to the pore sizes is limited to about 10 angstrom, like in the case of CO2. Molecular diameter of hydrogen is about 3 angstrom, which is about half angstrom less than nitrogen. This makes a difference in the characterization of microporous carbons. This slide shows the PSD results for 2 carbons introduced earlier in this presentation. It is clear that by using hydrogen, we expand the range of characterization of the pore size distribution to lower pore sizes. This may be important for the characterization of biochars and hard carbons for batteries. Here, we test the same approach that we presented before for nitrogen and CO2 analysis. We show that to save measurement time, we can measure oxygen isotherm without low pressure points. These points are not measured. And from the dual fit, obtain practically the same pore size distribution as in the case where the full oxygen isotherm was measured. Most of the presented results were related to the characterization of microporous carbons. In the recent work, the mesoporous templated carbons were studied. The series of mesoporous carbons were studied by CO2 and nitrogen adsorption isotherms. Based on the method of preparation and TEM images of the samples, we assume a dual shape slit-cylinder pore model for these carbons. We developed the new 2D NLDFT kernel for heterogeneous cylindrical pores based on the equilibrium model that describes the desorption branch of the isotherm. This branch is used for the analysis. Micropores, which are created by the carbonization process and then expanded by activation with CO2, are considered to be of slit shape, and adsorption of these pores is described by the 2D NLDFT model for the heterogeneous slit pores. The boundary between slit and cylindrical pore shapes is an important factor in the dual shape model. Traditionally, for nanoporous carbons, the slit cylinder boundary is assumed to be at 2 nanometers. This boundary is also fixed in the QSDFT hybrid model included in the commercial VersaWind software. In our approach, this boundary is an adjustable parameter. Now, it is logical to assume that the textural properties of our carbon samples change systematically with gradual activation. This should be reflected by a gradual systematic evolution of the calculated pore size distributions. We tried several values of the boundary parameter. We started with 2 nanometers and we increased its value until we reach systematic variation of the calculated pore size distribution for all samples. Figure 1 shows such systematic variation of pore size distributions. Clearly, the micropore peak broadens with increasing activation, and the mesopore peak, which is obtained by templating method, stays symmetrical and in the same position, but showing increase with increased activation. Figure 2 shows the pore size distribution for most activated sample using the boundary parameter of 2 nanometer. This assumption results in the artifact at about 2.5 nanometers. The same artifact is shown by QSDFT hybrid model that has fixed boundary at 2 nanometers. All presented models and more are listed on Micromeritics website and are available for download. Finally, I would like to mention one project which is in progress. I'm working with Jeff Kenvin on the dual gas model of hydrogen and oxygen for the analysis of ultra-microporous zeolites. Such zeolites that have 4 angstrom pores are really difficult to analyze with nitrogen or argon. Thank you very much for your attention.
Thank you, Jacek. I'm opening the chat for everyone's questions, and we already have a few questions from our attendees today. Just to be clear, in your dual gas method using CO2 and nitrogen, do you use just the CO2 for micropores and the nitrogen for the mesopores, or are you using them in some other unique way?
Well, this is done in a way that both isotherms, of course, they are measured separately. We are fitting them simultaneously. So there is a simultaneous fit of both isotherms with corresponding kernels. So this is how it was done. And of course, the single pore size distribution is obtained from this.
You also referred back to some IUPAC pieces and discussing argon and other fluids for adsorption. Specifically, why are you looking at CO2 and something like hydrogen rather than just using argon for some of these adsorption analyses and pore size distributions?
Well, in the presentation, I think I mentioned that argon is expensive in different parts of the world, which is in Europe, and so people try to use some other methods. So that's why we developed this modeling using oxygen, which can do the same, basically the same as argon, but it has smaller quadrupole moment than nitrogen, because the negative effect of nitrogen is interaction with quadrupole moment and some polar side. So this was the reason.
When using the oxygen, did you encounter any safety issues associated with using oxygen during the adsorption?
The safety issues, well, we have oxygen in the lab, and there is oxygen in hospitals. So of course you don't want to smoke cigarette next to the flow of oxygen. But I didn't notice any issues.
Okay, and I think the only time that oxygen comes into extra concern would be at elevated pressures and use with vacuum systems, and particularly if the vacuum system was using any hydrocarbon oil in the pump. In modern vacuum systems that use diaphragm or dry style pumps, don't require the additional concerns associated with oxygen. So as long as the seals and lubricants are not hydrocarbons, these oxygen does not tend to be a safety concern at these low pressures.
Okay, that's right. Probably we should put it somewhere, this information, for people to give them a good feeling on to use oxygen.
Jacek, your presentation has a lot of wonderful information on the modeling, and once you have the isotherm data and then calculating better methods for calculating pore size distributions, do you have any recommendation for experimental details for collecting these isotherms? Because again, we're using more than a single isotherm this time. So are there any special things users should worry about if they're going to collect a CO2 and a nitrogen isotherm, or a hydrogen and an oxygen isotherm?
Well, the recommendation would be to make this measurement on the same sample, because when we simultaneously split the kernels to these isotherms, and there is a small error in mass, this would influence the calculation. So it's good to have to use the same sample in the same setup, using both and measure both gases.
We've got a question now for relating to crystalline materials rather than carbons. Do you have recommendations for both probe molecule and the fluid, and the temperature for the fluid for zeolites, and then also for something like a metal organic framework, a MOF?
Well, the recommendation is kind of natural, is to use argon. Avoid nitrogen, because nitrogen has these interactions with polar groups, which are a lot of them in zeolites. Also, oxygen, I think, is I would recommend oxygen, because for the same reason as we talked about adsorption on carbons. But I think the very special case should be made for hydrogen, because for extremely narrow micropores like this chabizite, the adsorption with argon or even oxygen takes a long time and maybe never truly equilibrates. So hydrogen, because the molecule is smaller and we do it at supercritical conditions, then I would recommend using hydrogen for these extremely small pores. However, I still don't have the model, but I'm working on it, as you know.
We've got another really interesting, challenging question. In your presentation, you had really beautiful images that you were able to use to guide your choices on heterogeneity and structure, slit versus cylinder. What if a user doesn't have that type of information? How do they select whether it should be a cylinder or a slit when they use NLDFT and try to calculate pore size distributions?
Well, this you are talking about density profiles?
Well, just in general, if a user has an isotherm and they want to get to pore size distribution, do you have guidance for them as to should they choose a slit geometry or a cylindrical pore geometry? How do they know which one they should choose?
Well, this is a very difficult question. If we speak about carbons, usually the usual assumption is slit pore. But in my last slides, I show the case of templated carbons, and evidently they have cylindrical pores. The mesopores are of cylindrical shape. So we use this combination of two different shapes to, and then so we applied the slit for up to certain pore size. In this case, it was 30 angstroms, but it could be 20. And of course, the true pores are not perfect cylinders or slits. But there is, in terms of modeling, I think that for this kind of carbons, in the range of mesopores, especially if there is a hysteresis, then the cylindrical pore would be actually more appropriate.
Okay. The next, and there's probably two or three questions from this user, this morning's attendee. On the dual gas method, can you use the nitrogen and CO2 for materials other than carbon?
I would not use it for zeolite, but maybe for silica samples, if there is, then it could be used. But for now, we don't have the kernel, the CO2 kernel for silica. So, well, also
is the CO2
yes.
Does the CO2 have limitations with respect to materials? Should we only use it with carbons, or do you think it may be extended to be used with other materials, oxides or crystalline materials, with respect to characterization?
Right. So actually, the kernel that we have in our library was developed specifically for carbons, for CO2. I tried to develop a similar kernel for zeolites, but the interaction, because CO2 has very high quadrupole moment, then specific interactions overshadow the interactions related to pore size. So I wouldn't recommend using this, and we don't have it. Now, maybe for, so right now we just have only the CO2 kernel for carbons.
So the next question is a little bit focused toward the end of your presentation and things that are under development. Have you used this dual gas method for analyzing oxide particles, things like titania or silica or other materials?
I think I must admit that I did not for now. But who knows? Maybe we'll go to this material.
On the dual gas method, with respect to solving the diffusion problem, do you realize any benefits in the size range where you can probe? So, you know, if I just had an isotherm for nitrogen or argon, and I had materials with pores, with very small pores, maybe 4 angstroms, would I be able to get any reasonable pore size information for the nitrogen and argon, or does the CO2 give you a benefit?
CO2 gives the benefit due to the diffusion effect. So, of course, for small pores, diffusion is extremely slow. And sometimes we never reach for some samples, we don't reach the true equilibrium. So the isotherm is not, does not correctly reflect the real pore size distribution. So CO2 in this sense is better, may give better resolution and better results. In terms of size, hydrogen is even better than CO2 because it's smaller. Diameter of hydrogen is about 3 angstroms. So while CO2 is still about 3.6. And additionally, hydrogen is supercritical, so the diffusion is really significantly faster, even at 77 K, like liquid nitrogen coolant.
So this one, I think this next question is really specific to that point, and also from one of your last slides when you were talking about chabazite and 0.4 nanometer pores. Do you think the hydrogen, well, do you think there's potential for using the hydrogen oxygen or hydrogen nitrogen or hydrogen argon type systems down to 0.36 nanometers or potentially smaller with respect to zeolite?
Well, with respect to zeolite and the extremely narrow pore in zeolite, I think the best gas would be hydrogen. It could be combined with oxygen or argon in a sense, because as I mentioned in the presentation, hydrogen is only sensitive to very small pores below 1 nanometer. So in order to obtain full pore size distribution, it's good to combine hydrogen with argon or oxygen to describe the pore size distribution in full range of pore sizes.
For the hydrogen adsorption isotherms that you showed, do you need anything, since it's supercritical hydrogen, do you need any special equipment for the hydrogen adsorption isotherms, or can these be performed on something like an ASAP 2420 or a 3-flex or an ASAP 2020?
I use the 3-flex, and there is nothing special. We use the liquid nitrogen as a coolant for this. So the only thing is that some rules, safety rules, requires that hydrogen tank is in a safe place. But measurements are the same basically as argon or nitrogen. What is nice about hydrogen is that it absorbs much faster.
Okay, and there's one final question for this morning. We're just about out of time. This question, it may be a question, it may also be a request as I read it.
Are there any NLDFT models using the desorption branch, or do you foresee these being available in the future?
Well, most of the models that we have were developed for so-called equilibrium adsorption. So they can be applied to desorption branch. The question about using desorption or adsorption is about which model actually is representative for a given material. So if we have a perfect hysteresis, then we should rather use a desorption branch with the model with the same model basically. Well, for the models that like the 2D NLDFT heterogeneous surface models that we have are calculated by as equilibrium adsorption, and they can be applied easily for microporous carbons because there is no hysteresis and the desorption is the same as adsorption. So basically we have all equilibrium models.
Okay, thank you, Jacek. That's all the questions we have time for today. If we haven't been able to get to your question, one of our application team will be in touch with you shortly. Jacek, is there anything else you'd like to mention today?
No, I wish everybody a nice day today. Thank you.
Great. Thank you, everyone, for participating in today's webinar. If you have any feedback for us, we would be grateful if you could complete the survey, which we will distribute in a follow-up email. We hope you found the session beneficial. Do not forget to check back for upcoming webinars on micromeritics.com/webinars. We hope to welcome you again very soon. Thank you and have a great day.